Tresca would look into failure because of the shear, and he said that this failure because of the shear would happen at the maximum shear plane, and this is the sort of criteria you want to consider when you want to look into the failure. Now, the last criteria we are going to discuss today, and the last criteria we're going to basically discuss in this course, is called the von Mises criteria or criterion. This is a quite standard criterion for civil engineering, but also for aerospace engineering and for mechanical engineering. They use it in fracture mechanics as well. They call it the J2 criterion, and it is also known by different other names. So the distortion energy criterion, the octahedral stress criterion is just different names for the same thing. In this course, we are going to study this as the von Mises criterion. It is also available, I think, in pretty much all the finite element software. You will find the von Mises criterion. It's just called different names in different software. So the von Mises criterion would think that the material would fail also because of the shear. Now, according to von Mises, the material would only fail because of the shear, just like Tresca said, but the shear not at the maximum shear plane is going to be a specific shear plane. So a plane where this length is equal to this length is equal to this length. So if you think about it, is 1 over 1, 1, 1. And to normalize it, you just take 1 over square root of 3. If you normalize this vector, you'll see that the length of this vector is 1 over square root of 3. So you choose this plane, or you take this plane, you calculate the shear stress on this plane. Once the shear stress on this specific plane will arrive at a specific critical number, in this case, the material would fail. Before the stress or the shear stress on this very specific plane would arrive at this very specific critical number, the material would never fail. And you don't need to look at anything else. You only need to look at shear on this very specific plane. So this is what von Mises is concerned with. Now, again, is it realistic? It is realistic for ductile material, and it is realistic for quite a big range of alloys. And it is very useful for quite a few disciplines in aerospace engineering and mechanical engineering, also in structural engineering. Now, it is realistic under these scenarios, the sort of material properties I've mentioned. Apart from that, is not going to be relevant at all if you look into soils, for example. Okay, so now if you take this plane and you calculate the shear stress on this plane, I'm not going to get into the details of that, but you'll see that the shear stress will be 1 over 3 square root of sigma 1 minus sigma 2 squared, sigma 2 minus sigma 3 squared, sigma 3 minus sigma 1 squared. And just quickly, you get that from, you know that the principal stresses are going to be sigma 1, 0, 0, 0, sigma 2, 0, 0, 0, and sigma 3. You have this vector, you multiply this vector, and you get the stress vector on this plane. And then you have the stress vector on this plane. You can calculate the shear component of this vector. The shear component Ts squared is equal to Tn, the normal component of that, minus the length of Tn squared. Okay, Tn n and Tn s if you like. All right, so this shear or this vector, this stress vector will involve normal component and shear component. If you calculate the shear component, you'll see that this is the shear component. So the shear component is 1 over the square root of 3, sigma 1 minus sigma 2 squared, sigma 2 minus sigma 3 squared, sigma 3 minus sigma 1 squared. So this is the von Mises criteria. Now this would need to be equal to a critical number. Now what is the critical number? Again, in the uniaxial test, we have the stress tensor to be sigma 1, 0, 0, 0, 0, 0, 0, 0, 0. And we know that once sigma 1 will be sigma y, once sigma 1 will arrive at sigma y, the material would fail. So we feed this back into this equation. Sigma 1 is equal to sigma y minus 0 squared added to 0 minus 0 squared added to 0 minus sigma y squared. This is taken under the square root and multiplied with 1 over 3. And yeah, probably just write it down here. There is no space at the next slide. So this is 2 sigma y squared under the square root multiplied with 1 over 3. It is basically the square root of 2 divided by 3 multiplied with sigma y. So this is the critical number here. So the critical number will need to be equal to that. And if you go back to the equation and you take the square of this, so the square is, this square root will go away and you have 3 squared. You cancel the 3 with the 3, and the square root and the 2 will cancel with the 2, and you will be left basically with this one here. Yes, so you'll be left with this equation. So if you square the right-hand side and you square the left-hand side, the 3 will cancel with the 3, and you will be left basically with this equation. So for the von Mises, you can just compare sigma y squared to the difference between the principal stresses being squared. Okay, so this is the equation for the von Mises, and we are going to solve some examples on that as well. Again, if you look into this equation, you would see that it is only the difference between sigma 1 and sigma 2. So if you add P and subtract P, add and subtract, the material would never fail, and you will end up with the loophole, which we have discussed for Tresca. For the same problem with Tresca, you also have that with the von Mises. All the criteria which rely only on the shear would face exactly the same problem. So if you add the pressure to the principal stresses, you would never fail. However, if it is tension, it's going to fail because of the tension. If this is compression, it's going to bring the material stronger together, and it's not going to fail as quickly as von Mises would think. And if the pressure is huge, it's even going to fail due to the pressure, not the shear. Okay. So I'm going to discuss the yield phase, but let us solve an example. This example is the example which we have discussed earlier. So basically the hydrostatic pressure is minus Pi. So it is P multiplied with the identity matrix. If you add this to the principal stresses, then the material will never fail. So the failure would never change if you add hydrostatic pressure to Tresca or von Mises. So this is the type of discussion that exists in this example, and this is something I've discussed already for the 2 cases before. And this is another example. Where you have only shear and you want to test the failure according to the Tresca and von Mises. I'm going to solve this example as well. So you have the shear. Okay. So you have the stress tensor to be like this. And you want to test the Tresca and the von Mises. For the Tresca criteria, or for the Tresca criterion, you have sigma 1 minus sigma 3 divided by 2. And to be able to find sigma 1 and sigma 3, you need to find the eigenvalues. I probably just do this quickly here. Back. Okay, so it is minus lambda to 0 to minus lambda and 0, 0, 0, and minus lambda. if you find the determinants of this, make it equal to 0, you'll have minus lambda multiplied with lambda squared minus tau squared is equal to 0. So this would mean lambda is equal to 0, or lambda squared is equal to tau squared. And this would mean lambda is either equal to plus tau or lambda is equal to minus tau. So the principal stresses are going to be sigma 1 is equal to tau, sigma 2 is equal to 0, and sigma 3 is equal to minus 2. This is just the eigenvalue problem for this example. Now, if you want to look into the failure criteria, so for the von Mises or for the Tresca, you have sigma 1 minus sigma 3 divided by 2 should be smaller than sigma y divided by 2. And sigma 1 is tau minus tau divided by 2 should be smaller than sigma y. Or you have tau plus tau, this is 2 tau, and 2 tau divided by 2 is going to be tau. So tau would need to be smaller than sigma y for Tresca not to fail. If you look into the von Mises case, von Mises would take sigma 1 minus sigma 2 squared added to sigma 2 minus sigma 3 squared added to sigma 3 minus sigma 1 squared should be smaller than 2 sigma y squared. And sigma 1 is tau minus 0 sigma 2. This is squared. Sigma 2 is 0 minus sigma 3. This is plus tau squared. And sigma 3 minus sigma 1. This is minus tau minus plus tau. This is squared, should be smaller than 2 sigma y squared. This will cancel with this one, so you'll be left with 2 tau squared should be smaller than 2 sigma y squared. The 2 will cancel with the 2, and you will be left with tau smaller than sigma y. So as long as tau is smaller than sigma y, the material will not fail. This is pretty much exactly the same like in this. And if you look into the Rankine criteria, you will still also see the same thing. Rankine would only be concerned with sigma 1 should be smaller or equal to sigma ultimate or sigma y. And sigma 1 is equal to tau, so tau should be smaller or equal to sigma 1. So if the stress tensor is as simple as this case, so basically this is the uniaxial test, then in this uniaxial test, everything will need to be compared to sigma y. So sigma y should be equal to tau in order for the failure to happen, and sigma y should be larger than tau for the failure to not happen. All right. So this is the question, and I have one example for you to solve. I want you to solve this example now yourself. We have the von Mises, so we have the stress tensor to be given like this. I don't want you to go into the principal stresses. Don't calculate the principal stresses. I've given you the principal stresses here. And I want you to check the material failure using von Mises and Tresca. So for Tresca, you need to compare sigma 1 minus sigma 3 divided by 2 should be smaller than sigma y divided by 2. And for the von Mises, you also have the equation for the von Mises. So this is sigma 1 minus sigma 2 squared plus sigma 2 minus sigma 3 squared plus sigma 3 minus sigma 1 squared. And if you are going to calculate the safety factor, just take the square root of that, because you cannot take the safety factor taking the squares. So you need to be the square root of this. And then you have this to be smaller than square root of 2 sigma y squared. Shall we solve the example now? So the principal stresses are 13.1. Just use the board here. So sigma 1 is 13.1, sigma 2 is 5, sigma 3 is sigma 2 is minus 3.11. Minus 3.11, and sigma 3 is minus 5. Okay, so for von Mises, or for Tresca, to start with Tresca, we have sigma 1 minus sigma 2, or sigma 3, divided by 2, should be equal or less sigma y divided by 2. Now, sigma 1 is 13.1, minus sigma 3 minus 5, divided by 2. Now, at the yield point, we know that these forces are equal to sigma y divided by 2. So it is not smaller, it is equal to. So we get away, or we can cancel the 2. So this will make sigma y equal to 13.1 added to 5. So this is 18.1. And since this is given in megapascal, so this is also in megapascal. Now, if you look into the von Mises, for von Mises, you have sigma 1 minus sigma 2 squared added to sigma 2 minus sigma 3 squared added to sigma 3 minus sigma 1 squared. Again, is going to be equal to 2 sigma y squared. Sigma 1 minus sigma 2 is 13.1 minus 5, or so minus 3.1, this is plus 3.11, added to sigma 2 is minus 3.11, minus 5, this is plus 5 squared, added to sigma 3 is minus 5, minus 13.1 squared is equal to 2 sigma y squared. So this is basically everything in there. You just need to calculate sigma y. There is a square in here. So if you calculate these numbers, I think you have them in here. This is 595.6. So this number added to this one is 595.6 is equal to 2 sigma y squared. So sigma y is equal to 595.6 divided by 2 under the square root. And this is equal to 17.3 megapascal. So for von Mises, the yield is 17.3. For Tresca, this is 18.1. All right, I've got one last example for you to solve. So this example I'm not going to solve. I'm going to ask you to solve it. Evaluate. So basically evaluate the safety factor for Rankine. So what we are looking for is the safety factor for Rankine, Tresca, and von Mises. So what is the safety factor for each one of these? The yield is 300 megapascal, and the stress tensor is given like this. I mean, this is a picture of the stresses, and this is the stress tensor, and sigma y is equal to 300. So please calculate first of all, you need to do the principal stresses. You need to find the safety factor for ranking criteria, and then for Mises and for Tresca. So this example pretty much covers everything so far we have done so far in relation to the stresses. First of all, find the eigenvalues for this example here. So the eigenvalues for this stress tensor. Once you have the eigenvalues, I want you to apply the Rankine, the von Mises, and the Tresca criteria and try to find the safety factor for them.